Hey guys, today we're going to go through some definitions and learn some characteristics of linear and quadratic functions. So let's start with the definition of a polynomial. So just want you to understand what it means for something to be a polynomial. Poly usually means more than one. And in this case, it usually refers to something that has more than one term, although a polynomial could just have only one term. The big thing here, the big characteristic that's the most important for a polynomial is that the exponent that's attached to your variable has to be a positive integer. So you can't have an exponent that's negative, and you can't have an exponent that's a fraction or a decimal in order to be classified as a polynomial. So here are a few examples of polynomials that you actually should recognize. And we're going to actually do some investigation today into some details of the linear function and the quadratic function. So a zero function is just a function that is equal to 0, which would be a horizontal line that is right on top of the x-axis. A constant function would be something that's equal to a number. So let's say like y equals 2 could be a constant function. That would be also a horizontal line, but through the point 2 on the y-axis. A linear function is one where you have an x variable, but the power is only a 1, which is also the name for the degree. And a quadratic function, you guys know, is a parabola. All quadratic functions have a power of 2 as the highest exponent in the polynomial, which means that is also called the degree of that polynomial. So first off, just tell me whether it's a polynomial or not. So you're looking for positive exponents and not fractions and not decimal exponents. So in this one, this would be a polynomial, because all the exponents are positive and they are all integers, so not fractions or decimals. And it says in the directions, if it is a polynomial, to state the degree and the leading coefficient. Okay, so the degree is the highest power in the whole polynomial. So in this case, that highest power is 4. The leading coefficient would be the numerical value that is attached to the term that has the highest power. So this is the term that has the highest power. The leading coefficient, which is the number in front, is -9. The second example may be worth discussing real quick, that any radical can be rewritten as fractional exponents. So square roots are the same as raising something to the 1/2 power. So when I make sure when I understand that connection, then I know that I do have a fractional exponent, which means that this cannot be classified as a polynomial. Polynomials don't have messy fractions like that, so not a polynomial for this one. Example C, I see an exponent that is a negative, and that is not allowed for a polynomial to be classified as a polynomial term. So you would have another one where this is not classified as a polynomial. And then the last example, I do have exponents. They all appear to be positive and counting numbers and integers. I do have a fraction, but it's not an exponent, so that's okay. So this is a polynomial, for example, D. And because it's a polynomial, we're going to state the degree and the leading coefficient. So find your term that has the highest power, and that power is a 3. And the leading coefficient is the numerical value in front of that term, so -5. All right, so now we're going to dive in and kind of look at linear functions, which is a type of polynomial, a little bit deeper. So this is one characteristic that at this point in time you should be able to compute to describe a linear function. All of you should know this already because this is just slope. Okay, so y minus y over x minus x, that's slope. I've just got it written here 3 different ways because I want you to see that they are all equal, just different representations of the same computation. So y minus y over x minus x is what you guys are most used to, right? This is kind of like the regular way for finding slope. Delta y over delta x, that means change in y over change in x. Well, that change means subtract the 2 y values. So really this is just another way of saying find the slope. But this is typically, this notation is used in science. So you may see that this, this is like the science way of finding the slope. And then over here we have something a little untraditional, where we're, instead of saying y minus y, we're saying f of b minus f of a, and b minus a are the x values that are defined on your function. So remember, f of b, f of a, f of x, all that really just means the y value at that point. So this is just another way of saying y minus y over x minus x. But this is kind of like the way that you would see this in calculus. Okay, so this is the calculus way of describing slope. In the middle is the regular way, and then here at the end is the science way. I don't care which way you like best. I just care that you can find slope. So here's an example where we're going to do just that. And I think I'll probably do this the way that most of you are most comfortable, which is just the old y minus y over x minus x. So just a reminder that the number in parentheses is your x value, and the number on the outside is equal to your y value. So y minus y, I could do either 9 minus 3 or 3 minus 9, it doesn't matter. And then x minus x would be negative 4 minus 0. And just simply compute. So you get 6 over negative 4, which is equal to negative 3/2. Now, if you read the directions, it does say that our end goal is to write an equation in slope-intercept form. So just one quick refresher, slope-intercept form is y equals mx plus b. And m is the slope, and b is the y-intercept. So we do know the slope, we just found that value. The y-intercept is not given directly, but it is given. Think about where this point would be plotted had it been plotted on the graph. 0, 3 is that ordered pair. 0, 3 is on the y-axis, so that would be your y-intercept value. So you're going to take your slope and plug it in, take your y-intercept and plug it in, and you have your answer. Okay. Here are 5 different ways you can write equations of linear functions. And quite honestly, the first equation, general form, is almost never used, so you can just kind of ignore that. And down here, slope-intercept form and point-slope form. Those are the 2 you're going to see the most. Slope-intercept we just saw. Let's look at an example using point-slope. I'm going to write the formula up here one more time in case you are not familiar with it. But point slope is a form equation that we can use whenever we know the slope and we know a point on the line. Point slope. So if I know the slope and I know a point, I can use this setup. I don't know either yet. Actually, I do know a point, but I don't know the slope. So I'm going to start by finding that. So slope is equal to y minus y over x minus x. So in this case, 3 minus negative 5 would be the same as 3 plus 5. And x minus x would be negative 2 minus 4. So in this one, I'm getting 8 over negative 6, which simplifies to negative 4/3. So I have my slope. I can now write my equation in point-slope form by picking one of the 2 points and using that in place of the y1 and the x1. So I'll go ahead and use this first ordered pair, and I'm going to plug them in for y1 and x1, and then obviously slope is the number we just found. So that would look like y minus y1 is 3, m is negative 4/3, and x1 is negative 2, so I'm going to make this a plus 2. So there is one equation in point slope form. Now, you have two different points. So you could actually write a second equation using the other ordered pair, and it would be also a totally acceptable answer because both are using a point that exists on the line. So either one of these would be fine. Now, some of you are probably sitting there scratching your head thinking like, why on earth would there be two possible answers? Well, that's because both of them simplify down to be the same thing. So let me copy down my first equation and show you what I mean. Actually, I'll go ahead and put both of them on here so I can work with both. So I have these two equations that are supposedly the same, right? Even though they have different numbers and don't look anything alike. I'm going to prove to you that they are both the same equation and represent the same line by solving for y. So I need to do -4/3 times 2, which is -8/3. Add 3. So I'd have y equals -4/3 x. And then -8/3 plus 3 would be -8/3 plus 9/3, so 1/3. Okay, this is one equation in slope-intercept form. Let me solve the other one now. So I would have -4/3 x plus 16/3 minus 5. And then I would get y equals -4/3 x. 16/3 minus, that would be 15/3 is 1/3. So you see when you get your equation in slope-intercept form, you do have an identical match, which means these two equations do represent the same line. Okay, that's it with linear functions. Now we're going to talk about quadratic functions, which remember these are just parabolas, okay? Parabolas and quadratic functions have two different forms. You can write it in standard form, which is what we see most of the time, or you can write it in vertex form. Vertex form is incredibly useful because it separates everything so that we can very clearly see the transformations that have occurred with that parabola. So remember, like the number, if it's x minus h, that would mean it went left h units, up k units, and then this number on the outside is like a vertical stretch. It also tells us where the vertex of that parabola would be located. So the vertex of the parabola would be located at the point h, k. And that just means like the vertex is where the minimum or the maximum value is located. So like this. This is the vertex, which can be super helpful if it's in this format. A couple other things about parabolas and quadratic functions. The axis of symmetry is kind of like finding the x value where the vertex occurs. Okay, so this is identified as h, which is the part of the vertex, so the x value in the vertex. You could also find this by doing -b over 2a if you were in standard form. We also have the quadratic formula coming back. We'll use that in a few minutes. One other thing right here. When it says opens upward, opens downward, what that means is if you have a parabola that looks like a smile, like this, that's called opening upward. And if you have a parabola that's going down like a frown, that's considered to be opening downward. This a greater than 0, a less than 0 is referring to the a value at the beginning of each of your different forms for your quadratic function. So all we're saying simply is if that a value is positive, you're going to have a smile kind of parabola. If that a value is negative, you're going to have a parabola that's flipped upside down. All right, this should be review for you at this point because it's just asking for the transformations that have occurred from the parent function to this thing. So when we see a negative, we know that that means reflection. And you can reflect either over the x or over the y. Well, since this is on the outside, it's going to reflect downward, which means it's going to go over the x-axis. The 1/4 on the outside will represent a vertical compression or shrink. The -2 on the inside will make your graph go to the right 2 spaces. And the 3 on the outside will make your graph go up 3 spaces. That was really easy to do because I had my equation in vertex form. But what if it isn't? If your equation's not in vertex form, you're going to have to use completing the square to put it in vertex form. So I'm going to very quickly remind you what completing the square is, although I am told you did do this last year. To start with completing the square, I need to go back a step and make sure you understand how to do the binomial square shortcut, which is basically just squaring something like a binomial in your head. It's a 3-step process, okay? Step 1, square the x, which would be x squared. Step 2, multiply these 2 terms and double it. So x times 5 is 5x, doubled is 10x. And then step 3 is take 5 and square it, and that would be your resulting solution. Okay, when we do completing the square, we're kind of reversing that step. So my end goal is I want to have x plus something squared. I want that to be the way that this gets factored down. So I have to figure out what this number would have to be so that this binomial squared is equal to this, okay? Now, as I told you in the steps, to find the middle term, you took these 2 things and doubled it. We're going backwards. So if I already know the middle term, I'm going to take half of it, and that's going to equal these 2 things. So I'm going to take half of this, which would be 1. And that tells me that this would have to be a 1. So multiply this and double it, and you get 2. Now, if I know this number, then I know from the shortcut that I just need to take this thing and square it to find that third number. So I'm going to take 1 squared, and that tells me that this number would have to be 1. Let's try again. So the shortcut way would be take half of the middle term and square that value, and you get your third term. Then, if you have to factor that trinomial, you would take the number that goes here would be equivalent to half of that middle term, which is -2. Try again. Half of the middle term, square it, and you get 16. So that is a perfect square. And then factored, you would take either the square root of 16 or half the middle term, and that would be 4 in this case. It is possible to find your third term for it to be a fraction. So I'll just do this last one here. Same procedure. Take half the middle term, but we're going to leave it as a fraction. And then square that value, and you get 9/4. If you then have to go and factor that trinomial, remember that this number is always going to be the half of your middle term value. So it is -3/2 in this case. Okay, so let's start with a simple equation where we are solving by completing the square. And then I'll show you how to use this to do something more complicated. So essentially, I want to solve this equation by factoring, but it's not possible to factor the way that it is right now. So what we're going to do is we are going to take the constant term, which is 3, and we are going to move it to the other side. and you have to add 3 to move it to the other side. In its place, you're going to put a blank. This is where you're going to apply the completing the square process. So you're going to take half your middle term, square it, and that's going to tell you what number to plug in here. And you're doing this so that you could create something that is factorable. Now, you just plugged a 9 into an equation where there wasn't a 9 before. So to balance this equation back out, I need to put a 9 over here as well. Okay. Now, your next step is going to be to factor the trinomial you have just created. So this one would factor to x, and down here is my little clue, which is minus 3 quantity squared. On the right side, I'm going to add 3 and 9. My goal is to solve and find x, so I'm going to next take the square root of both sides, which would give me plus or minus radical 12. X minus 3 equals that. And then add 3, and you are finished. So x would be equal to 3 plus or minus radical 12, although it might be nice to break radical 12 down and call it 2 radical 3. Okay, now completing the square can get a little bit messy when you have a number in front. So in this particular example, I do have a number in front, and it's not factorable with a 2 in the front. So I'm going to go ahead and take the 2 and divide the entire equation by 2. Everything is still balanced because I did divide everything by 2. Now I'm going to try to create a perfect square trinomial by using completing the square. So I'm going to subtract the 5 halves and move it to the other side. And I'm going to figure out what my middle term would need to be. So half of the middle term is half. And if you square that, you get a fourth. So I need to add 1/4 to both sides to make sure my equation remains balanced. Your next step is to factor the trinomial you have just created. So factoring would make it look like y plus 1/2 quantities squared. I do need to add negative 5 halves and 1/4, so I need a common denominator first. And it looks like I'm going to get negative 9/4. Okay, square root both sides. Here's another little roadblock. I have a square root of a negative. So from last year, hopefully you remember that square rooting a negative gives you an imaginary number because it's not computable. And also, I can actually take the square root. I didn't catch that. I can actually take the square root of 9/4 because the square root of 9 is 3 and the square root of 4 is 2. So this would become 3 halves. And I'll just put my I over here. Subtract 1/2 and you are finished. So I do have an imaginary number as my solution for this question, which is okay. So just beware that that could happen to you. All right, one more question, and then we will move on to the quadratic formula very quickly. So here is a different example where we're going to use the technique of completing the square, but our goal is not going to be to use it to solve an equation. Our goal is going to be to use it to rewrite an equation in vertex form. So watch closely. Notice that my equation does not have an equals 0. So I will not be following the process in the exact same manner. I am going to start by getting rid of this 2, but again, because I don't have an equals 0, I cannot go through and divide everything by 2. I have to make sure that everything remains algebraically equivalent to this original function. So what I am going to do is I'm going to factor out a 2 from every term, from every term except for the last term. And where the last term was, I'm going to put a blank so that I can make this thing a perfect square. So the last term, I'm just going to slide it over to the outside of that parentheses. Okay, now think about what we've done. We did factor everything out. And now the -1 is still here, so this whole thing is still algebraically equivalent to what it was at the beginning. Now I want you to complete the square, half the middle term, and square it, and you get 1. Okay, now what I have is not algebraically equivalent to what I started with because I put a number in that did not exist before. What I need you to think about really closely is that the number that I put in is not actually a 1 because it is inside of a parentheses with a multiplier on the outside. This 2 on the outside gets distributed all the way through this parentheses, right? Which makes this number into a 2. Now, you have added 2 to an equation where there wasn't a 2 before. You have to balance that out. The catch is you don't have a 0 on the other side of the equation to move it over to. The way you're going to balance that out is by doing the opposite of adding 2. So you are going to subtract 2 to take you back to where you were originally. That is difficult, so take your time and think about that step. The next thing to do is to factor the trinomial that you have created. In this case, it would be x plus 1 quantity squared. And I'm going to go ahead and do -1 minus 2 and call that -3. And that is it. You have just created your same function, but in vertex form. So that means that you can use that to describe the graph. You could say that the vertex is located at -1, -3. That's what these values here represent. You could also say that this was a parabola shifted left 1, down 3, and stretch vertically. You could also have enough information to actually make the graph. So for your parent function, you got a parabola that's right about here. I'm not getting super detailed, just a quick sketch. So there's your parent function. And our function was moved with a vertical stretch of 2 and left 1 and down 3. And the only reason, again, that I know that is that my function was in vertex form, which gave me more information about the parabola and what it was doing. There you have it. Okay, something that I did for the students in class is I did a demonstration to show how the quadratic formula was created. Just simply to kind of make sure they understood that, like, not very many things in math are just made out of thin air, and a lot of things were developed from standing information. So I have that on the next slide for you, and I'm just going to make sure you understand that a couple things. So obviously when you look at this, you're like, oh my, that's so overwhelming. And you're right. But really all this is starting with the standard form of a quadratic formula, quadratic equation, and completing the square to turn it into the quadratic formula that you use so frequently, okay? So if you'd like, I could always go through this in detail in another video for you. If that's something you want to see, just reach out and let me know, and I'd be happy to do that. One more example, completing or solving the equation using the quadratic formula. So the quadratic formula is something you should be familiar with at this level. Because I believe you use it in Algebra 1 as well as Algebra 2, maybe even geometry. But we're going to make sure that we understand it and feel comfortable with it before leaving this section. So the formula itself, remember there's a little song I think that Mrs. Young sings to remember the quadratic formula, but this is it. This is the formula there. And all I have to do is identify my A, B, and C values and then plug them in. So B is -1. B is 1, but I have negative B at the beginning. And then I need B squared minus 4 times A times C, all divided by 2 times A. So I would set it up like this, and I would start working through to simplify under the radical first, which that would be 1 plus 12. And maybe just like 2 more steps, I could add 1 plus 12 and make it 13, which does not simplify. And then we could also just state that this does represent 2 different solutions, one with a plus sign between and one with a minus sign between. So you have 2 different answers for this quadratic equation.